My name is Jonas, and I wrote this short paper together with Nicholas Katzakis. Starting off, what is our motivation here? You can see we have a human-robot interaction scenario right here. And in contexts such as virtual reality and human-computer, human-robot interaction, pointing is actually a very intuitive and effective tool to issue spatial commands. And because you don't have any kinds of keys or macros, it is very useful to add hand postures in order to give expressivity to pointing. So when designers have to decide on which hand postures to choose, they have to look at which are best for performance and for user experience. So the problem we're seeing here is that if designers want to evaluate hand postures, they either have to do it very subjectively by simply saying this posture is bad, this posture is good, or they have to do very work-intensive user studies. And we assume that hand posture comfort and discomfort does affect performance and obviously user experience. So this is why our goals were to, first of all, create a metric for quick and objective hand posture comfort and discomfort evaluation. And second of all, we wanted to show that comfort and discomfort as measured by a metric does affect performance in a pointing-based environment. So before we started creating this metric, we've had to have an exact definition of comfort and discomfort, and we used the one of Winkedal, who defines comfort as a pleasant state or relaxed feeling of the human being, which is influenced by subjective impressions and expectations. Discomfort, on the other hand, is an unpleasant state of the human body, which is caused by physical stress. So it's important to know that these both, comfort and discomfort, they are not the opposites of each other. They are, in fact, independent from each other. Just so you know. So before we started, we looked at some other things that have been done in this area. And we first stumbled across Apostolico et al., who introduced the term range of rest posture for human joints, which I will talk about more later. And then we had Nadio et al., who took this range of rest posture and proposed a quantitative method for postural comfort evaluation using this. The only drawback on this is it only looks at comfort, so we don't have any discomfort in here. And the complex of creating such curves, as you can see them here, is rather complicated. So this is why we decided to make our own metric. And we identified 4 main components that we believe to affect hand comfort and discomfort the most. And I will explain those shortly. First, we have the deviation from the range of rest posture. Then we have interfinger angles, finger hyperextension, and finally finger abduction. So starting with the deviation from the range of rest posture, as Apostolico defines it, every joint has a so-called rest posture, and this is the relaxed posture of that human joint. And when in that posture, maximum comfort is perceived. This also means when you deviate from this posture, perceived comfort levels should decrease. And due to anatomical differences between different people, it makes sense to talk about a range of rest posture, which simply is an angle range for joints, where the joint can be seen as statistically in rest. So in our case, we had to look at the RRPs for all joints in the human hand. Moving on, we have the interfinger angles. As you can see here on the right, we have a relatively complex hand anatomy where most finger flexors and extenders share the same muscles. And you even can see we have interfinger tendons on the back of the hand, which of course limits the individual finger movement. This, on the other hand, means that high interfinger angle differences, such as this, create high stress on the tendons and on the muscles, and we therefore suspect this to create large amounts of discomfort. Moving on, we have the finger hyperextension. As Laviola puts it, hyperextension puts more strain on the joints and tendons than the hand is accustomed to. And we have high stress. We have high stress on joints, tendons, and muscles, which we suspect to create discomfort. Moving on with the finger abduction. So this was chosen analog to hyperextension because high abduction rates create stress on the joints, tendons, soft muscles, and even the soft tissue in between the fingers, which we suspect to produce discomfort. So after we had identified these 4 components and thought about how we compute them, we had to think about how to combine these into one big metric. And first of all, we had to make sure that these metric components are comparable. So we gave, so every single of these components has a metric value of 0, which stands for maximum comfort or minimum discomfort, respectively. And increasing values stand for comfort, which decreases, or increasing discomfort. Then we decided to simply add up the different component values, and as they might scale differently, weight them with importance coefficients. So using this, we created our very first metric, the naive metric, where we simply add up the whole hand component values with empirically estimated importance coefficients. And this is a simple first implementation, and it gives us a good rough estimate on comfort and discomfort level in a hand posture, and we use this later on in the process. The only problem with this is it completely ignores the anatomical differences between the individual fingers. And why this is important, you can see if you point on something using the index finger and point on something using the ring finger. I don't see anyone doing this. Okay. So this is why we decided to improve our metric. And for this, we would simply compute the metric components for each finger individually and give them their own individual weighting coefficients. And instead of estimating these coefficients, we decided to simply collect data in a user study with help of the naive metric and use the least squares algorithm to find the optimal coefficients. So as said, we wanted to do a user study, and we had 3 objectives for this user study. We wanted to gather data for the improvement of the metric. We wanted to verify that the improved metric that we created is actually a reflection of perceived user comfort and discomfort. And we wanted to show that comfort and discomfort, as measured by a metric, in fact does affect performance in a pointing task. So we created a user study with 2 different tasks in Unity 3D. Task number 1, which would be a hand posture rating task. There we would generate a random hand posture, as you can see here. We would check it with the naive metric to see if it's in certain bounds of comfort and discomfort, and we would show it to the subjects. The subjects would then have to reproduce this hand posture using their dominant hand, and after a short amount of time, they had to rate this hand posture on an intuitive comfort or discomfort scale, ranging from 0 to 10. 0 would be the worst, and 10 would be an absolutely comfortable hand posture. Then we had a second task, the target shooting task. Again, we would show the subjects a randomly generated hand posture, and again, they had to mimic and rate this hand posture. But after that, they had to perform a target shooting task using exact that hand posture. And we tracked the hand using OptiTrack and tracked the hand posture using a leap motion controller to make sure that they would hold the posture throughout the experiment. And as a measure for performance, we measured the total task completion time. So we had a main user study where we did several rounds of hand posture ratings, which was used for improving the metric. And we also had some rounds of target shooting, which were used to investigate the impact of comfort and discomfort on performance. And finally, in order to verify that the metric in fact does reflect perceived user comfort and discomfort, we did an extra round of hand posture ratings. And you can see the results of this rating right here. You can see on the x-axis you have the user ratings, on the y-axis the improved metric values. And you can see that higher metric values cause the users to rate the hand postures worse, which is exactly what we expected. And doing a statistical analysis using the Pearson correlation showed us that we have a significant, strong correlation here, which means that improved metric in fact does reflect the perceived user comfort and discomfort. Moving on, we have the results from the target shooting task. Again, we see that high metric values create longer total task completion times, which is confirmed again by a significant strong Pearson correlation, which again indicates that in fact comfort and discomfort do affect performance as we predicted it. But as you can see here, we didn't have 2 big dimensions in our user studies, so we need to do more work on this front in order to make strong conclusions here. So wrapping everything up, we wanted to create a comfort-discomfort metric for quick and objective hand posture evaluation. We improved this metric using data from a user study. And finally, we verified the metric in a testing user study. We also wanted to show that our metric is important by showing the effect on the performance in a pointing-based environment. And this we tested in a target shooting task, and the results indicate that, in fact, comfort and discomfort as measured by a metric do affect performance. However, we need to do more work here to make strong conclusions. So what did we do wrong, basically? So our metric combines comfort and discomfort, and seeing that those are two independent things, it's maybe not the best thing to do. And we also only looked at short-term effects. So as a next step, it would be very interesting to look at comfort and discomfort effects separately and to investigate their effects in short-term and long-term contexts. And this was also our very first model, so it would not be too bad to have a better model. So that's it from my side. Are there any more questions?
Kyle Johnson from the University of Georgia. It's very interesting work. So when you started doing this, I was wondering if you, given your model, tried to enumerate all the different hand positions, and did you discover one that might be more comfortable that you never thought of?
So we tried just not to do this because in the end, so the most comfortable hand posture that we found was the rest posture of the human hand, which is something like this. It's unbeatable in terms of comfort and low discomfort. But what we didn't try to not to do was to enumerate hand postures, simply because we didn't want to miss any hand posture. So yeah, I hope this answers the question somehow.
Thanks.
Okay. Anyone else?
Any more questions? All right, then let's give another hand to the speaker.